So I'm getting ready to melt some ice here and track the temperature and the time just to see how temperature responds as we're going through the process of melting the ice. So I've got a block of ice. It's frozen into a temperature probe actually. I've got a computer that's tied to the temperature probe through a piece of lab interface equipment. And I've got this all set up above a burner, which I'm not going to use right now, but I just wanted to have it in place in case I want to add energy faster later on. And so basically what we're going to do is track how temperature responds to energy input. I'm zooming in here so you get a better look at the actual ice as we go through this process. So we're looking right at the block of ice inside of a beaker right now. So if we think about the old LOL chart, at first we've got energy stored as E therm. That's the only real storage mode that we can think of here. It's not kinetic or gravitational or anything. We're adding energy from the outside through heating because the air is warmer than the ice, and that results in an increase in E therm, as we can see by the increase in the temperature that we're seeing here. Looks like the temperature flattens out for a little while, and then it rises, and then the temperature begins to come back down. Each one of these temperature points on this graph represents 30 seconds in real time. So this is sped up about 20 times. The video that you're watching took about 2.5 hours to record in real time. So what's going on here is we're continuing to add energy because the outside air temperature is still higher than the temperature of the block of ice. But even though we're doing that, the temperature is not going up, which is a little bit strange. In fact, this is a lot strange. When you think about the LOL chart, what we've got here is we had some energy as E therm when the ice had reached 0 degrees. We're continuing to add energy through heating, but the E therm is still the same, which means we added energy, and we should have more energy when we're done. So this is a weird thing. We don't have an answer for this at the moment with our model of energy storage and transfer. In fact, the answer is we have to think of another way that energy can be stored in a sample of matter like this ice. And that is something called E phase. It turns out that it takes more energy, or more energy can be stored in the particles when they're in the liquid phase. When the particles are separated from each other, they're no longer locked into a crystal position. There's more energy stored in that arrangement. And we call that E phase. So we start out storing some energy as E therm and some energy as E phase. And then as we add energy through heating, because of the outside air being warmer, we're not storing that energy as E therm, and that's why we see the temperature remaining flat. Instead, we're increasing the storage as E phase. So liquid stores more energy in E phase than solid does, and that's what the energy is being used to do right now. This is quite a long period of time here. It's going by 8 times speed, but it's still really slow. So when this would happen in live time, this flat spot on the graph here is well over an hour of time. Every once in a while you can see there's a little wiggle in the graph, and you'll see a couple of visible blips here. What's going on there is as the ice melts, the temperature probe occasionally slips out of the ice and starts measuring air temperature a little bit more than it's measuring the temperature of the water and ice mixture that's now in the beaker. So I swirl it around a little bit, and sometimes I have to adjust the temperature probe. But basically what's happening is the energy is still continuing to be stored as phase energy, not as E-therm. Because the temperature basically is remaining flat. Piece of ice is gradually getting smaller now. And as the ice breaks away from the temperature probe and starts floating around the beaker, I'm getting more of those blips because there's getting to be some hot spots inside or warmer spots inside of the water as the ice floats away. So I continue to swirl it to try to keep things equalized inside that beaker. Ice keeps getting quite small now. A few more of those blips here. As the ice cube really becomes quite small. And at this point I'm adding a flame just to speed things up. So energy is being added, but the temperature is still remaining pretty constant while there's still ice in the beaker. And now the ice is just about completely gone, and we see a change occurring. Now the temperature is beginning to rise here. So let's go back to our LOL chart. What's going on here is, since we're seeing the temperature increasing, that means that as the energy is being added from now the burner, in addition to the outside air, the temperature is rising, which means E-therm is going up. But it's liquid water before it begins this rise, and it's still liquid water now, so there's no change in E-phase, because the phase is still the liquid phase. So all the energy now is being used to increase the temperature, which we see as an increase in E-therm in our model. And now as we reach 100 degrees, we're at the boiling point of water. This is another phase change. So as we add energy through heating from the burner, the temperature is again continuing not to rise. And it's going to settle in at 100, and it would stay there for a really long time. We're going to stop filming at this point. So the energy is being added, it's increasing E-phase as the water boils, but the temperature is staying the same, and so we see E-therm stuck where it is because the temperature stays at 100 degrees C.